Okay, so we're going to talk about the central limit theorem. This is an idea in statistics. Here's what it says. It says you've drawn SRS of size n from any population with mean mu of x and standard deviation sigma of x. And notice this is any population here. That's the important language, meaning that it doesn't have to be a normal distribution necessarily. When n is large, the sampling distribution of the mean of x bar, the mean of all each individual sample, is close to a normal distribution with mean mu of x and standard deviation sigma of x over rad n. So sometimes we write it this way. We say that mu of x bar is equal to mu of the population, and the standard deviation of x bar is equal to the standard deviation of the population divided by the rad of the sample size. So this happens when n is large. Now that's sort of vague. What does it mean for n to be large? Depends on textbooks you're reading. Most of the time they say between 30 and 40 is usually large enough to get a sampling distribution which is approximately normal. So let me demonstrate this with the following. Okay, so let's consider a normal distribution to start with. So we have a normal distribution and it has a mean of 16 and a standard deviation of 5. And what we could do is start to create the sampling distribution. Now, let's consider n just equal to 2 for now. And if I hit 5 and I take 5 samples, you'll see the distribution starting to form here in the bottom. There's another one. That's the actual sample of 2, and there's the mean. If I hit 10,000 or 100,000, what you start to notice is that this thing on the bottom starts to look like a normal distribution. Well, n was 2, which is a very small sample size. So the standard deviation of the distribution is 5 over the square root of 2, the standard deviation of the population divided by the rad of the sample size. But you also notice it's normal as well, just like the original one was normal. However, if I change the original distribution to something that's skewed, and then I keep the sample size at 2, and I do 100,000 trials, or 200,000, or 300,000, here's what you start to notice is the blue distribution on the bottom does not look normal. It's definitely skewed, just like the original one. And that's really because the sample size of 2 is not large enough. Let's go back to central limit theorem for a minute and read this again now. Here's what central limit theorem tells us. Okay, I'll minimize this actually. Okay, so central limit theorem says you draw an SRS of size n. In our case, n was 2. And the key language here is this. When n is large, you can expect the sampling distribution to be close to normal with the following mean and the following standard deviation. Well, what this picture just demonstrated was that n equals 2 was not a big enough n. So let's try changing this. Let's take n and let's make it 16 instead. And again, we're still drawing from a skewed distribution, but if we draw, say, just 10,000, and you look at the picture on the bottom there, what you'll start to notice is here 100,000, 300, 400,000. That distribution on the bottom, not only does it have a smaller standard deviation than before, but it looks normal, and you can see I fit a normal curve to it. So n being 16 made the sampling distribution closer to normal than n equals 2 did. N equals 2 didn't even achieve that. Let's try an even bigger sample size. Let's try 25 and try 100,000 samples. And what you'll notice is you get a nice symmetric histogram down on the bottom there. So that leads us to believe that this thing's even closer to normal. So that's what the central limit theorem says. If n's large enough, then we can expect the sampling distribution of x bar to be approximately normal. Okay, and because of that, we can answer probability questions even when an original distribution might not be normally distributed. Okay, so maybe we should practice one. So let's consider an example where you have a machine that makes a particular axle for a part of a car. And let's pretend that the x is going to be the radius of a single axle. Produced by this machine. Okay, so let's pretend we're told that we know the mu of x, the average of these axles, is 40.235, and let's say it's measured in millimeters. And then let's pretend the standard deviation of these measurements has been about 0.003 millimeters. Okay. So If they don't tell us that the distribution is normal, then we can't really answer any questions about probability. So for example, it might be the case that the producer of this is worried. They're saying, hey, look, anytime the axle comes back larger than, let's say, 40.3, or x is less than 40.1, then the axle can't be used. It's going to be, the diameter is going to be too far away from the target diameter, and we're going to have a problem. Now, if we don't know the distribution is normal, then we can't answer this question. However, if we're told the distribution is normal, then we can start to answer this question. So let's pretend the distribution of axles, or x, is approximately normal with a mean of 40.235 and a standard deviation of 0.003. So we can now ask probability questions. So let's find the probability that x is greater than 40.3 or x is less than 40.1. Well, we can graph that on a normal distribution and get a sense of what the areas we're interested in. So here we go. Here's the normal distribution with the mean of 40.235 in the middle. Now, it would be nice to, let's try and get z-scores for these numbers. I'd like to change this probability to something like this. The probability that z is greater than something or z is less than something. That would be ideal. So let's try and do that. Let's go back to the calculator. So, hold on a minute. So here we go. We'll quit out of this. We'll go to the home screen and clear. Okay, and here we go. So our first number was we were worried about is 40.3. There it is. And we have to subtract that mean and divide by that standard deviation to create the z-score. So here we go. So 40.3 minus 40.235 equals that, and we'll divide by the standard deviation of 0.003, and we get a z-score of 21. Actually, you know what? It would be more interesting if this question had a z-score of 0.03. I mean, a standard deviation of 0.03. Let's just do that. Sorry to change it on you, but it'll be more interesting. Okay, so let's go back here. So really, it should have been 0.065 divided by 0.03, and we get 2.116. So that's what this one is, 2.166. Okay, and then we also have to do the same thing for the 40.1 to get that z-score. So let's do that. So we'll do 40.1, not divided by, sorry, minus 40.235 equals that. And then we'll divide by 0.03, and we get a z-score of -4.5. Okay, so this is pretty far away in terms of z-scores. So here we go. Here's a z-score of 2.166 is up here. And a z-score of -4.5 is very far down below the mean. And we know from looking at normal distribution charts that that area is almost zero. So this area is going to be negligible. Okay, and then here, this area we can get using normal CDF functions. Let's do that. Second distributions, we'll go to normal CDF. The z-score we had was 2.166, comma, up to a huge number, comma. When you're dealing with z-scores, the mean is 0 and the standard deviation is 1. Hit enter, and we get an area about 0.015. 0.015. Okay, so this is not very likely to occur. That's good. That means that this machine is producing axles that are going to be usable. Okay, so what typically happens with these machines? Well, I can tell you that usually they get inspected from time to time, and maybe you'd be worried that the machine isn't producing axles close to this diameter. This is the diameter that you really want to have here. So maybe you're worried that it's higher or lower or something. So here's something. We know we can't use it if it's 40.3 or higher. So let's find the probability that x bar, the average, where the sample size is 10, is greater than 40.3. So let's pretend an inspector comes along, he pulls 10 axles off the assembly line and finds the average, finds the length of all of them and finds the average, and it turns out that the average is 40.3. And the question is, does that imply that the machine isn't working properly? So we're going to convert this to a z-score, but we got to be careful because now we're talking about a new distribution. We're talking about a sampling distribution. And sampling distributions, the distribution of x bar, is approximately normal with a mean of 40, our mean was 40.235, and a standard deviation of the population divided by the rate of the sample size. So that's what our distribution looks like. Now, we don't need central limit theorem in this problem because, first off, 10 is not really a big number, so that's not a big value event, so central limit theorem probably doesn't apply. The other reason we don't need it is because we knew the original population of wheel axles was normal. Now, if we didn't know that, then we'd have to hope that n was big enough so the central limit theorem would apply. So we'll talk about that in a minute. Let's finish this off. So this is going to be 40.3 minus 40.235 divided by 0.03 over the square root of 10. And that's what we're going to find the area of. I'm going to do a normal CDF to get that to work. So second distributions, normal CDF. You've noticed I didn't calculate that z-score, so I'm going to do this. I'm worried about the area being bigger than 40.3 to some massive number, comma, the mean of the distribution is 40.235. So when you don't use a z-score, you can type in the actual mean. And the actual standard deviation will be 0.03 divided by the square root of 10. Oops, hold on, let's delete that. Okay, and here we go. Close parenthesis, enter, and we get an extremely small area, basically 0. So this area, this probability is coming back at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 with a negative 12 power. Wait, hold on a second. That's 3.67. So this, 367. So basically what this probability is telling us is that the inspector should never expect to see a mean of 10 axles coming back at greater than 40.3 millimeters. So if in fact he did observe this, he would have to say, wow, something happened here that really shouldn't have happened, and therefore conclude that this machine is not producing axles with a mean equal to 40.235. Now, I haven't stated null hypothesis and alternative hypothesis yet. I will get to that, but this is just to give you the idea of what's called a hypothesis test, or what it means to be statistically significant. Okay? So statistically significant result here, we found something very rare. Now, let's sort of redo the problem. Let's pretend that, again, we have a machine that's producing axles with a mean like that and a standard deviation like that. But let's pretend we're not told anything about the shape of the original distribution. So what do you do? Well, you can't answer this question. The probability that x is greater than 40.3. In other words, the probability that a single axle is greater than 40.3. You can't answer that, and that's because you don't know what this distribution looks like. It might actually be skewed somehow, or it might be a uniform distribution. So since we don't know the shape of the distribution, we don't know what to find the area. Are we finding this area? Are we finding an area like this? It would be different depending on the shape. However, if we take a large enough sample size, so suppose we take a sample size of n equals 30, then that would imply the distribution of x bar is approximately normal with a mean of 40.235 and a standard deviation of 0.03 divided by the square root of 30. And that's true by central limit theorem. So central limit theorem, that can be proved, by the way, with calculus. But central limit theorem is a very powerful theorem. It actually helps us find probabilities in questions where we don't know anything about the distribution of the population, but we can say something about the sampling distribution. So in this problem, we can ask, hey, what's the probability of x bar? being greater than 40.3. We can do that because that's really just the same thing as the probability of z being greater than 40.3. Oops, hold on a second there. 40.3 minus 40.235 divided by 0.03 over the square root of 30. And if I found the area, by the way, that area turns out to be basically 0. It's very unlikely. But we can do that now, and that's because we know the distribution of x bar is normal. And that is the power of central limit theorem. Thanks for watching.